This is Geometry Unit 9, Lesson 1, Introduction to Trigonometry. Trigonometry is the study of the measurement of triangles. So what we are going to be looking at is specifically right triangles and different values that we can use to find like angles and sides of the triangle. Now, when we use trigonometry, it's very important to know in a right triangle what all the parts are when we're relating to the sides and the angles. So, here's my picture. Triangle ABC is here, where C is the right angle, and A and B are acute angles. Now, the sides that we need to know. The hypotenuse is the longest side. It is across from the right angle. So if my right angle is here, AB will actually be my hypotenuse. So AB is my hypotenuse. Now, when we are talking in trigonometry about opposite and adjacent, you have to be looking at one of the acute angles and where the sides are in relation to that. So, the opposite side is the leg that is across from a given acute angle. So, if we are looking for the side opposite angle A, right here, that side would be opposite it. So, this side is opposite angle A. That is side BC. Now, the side opposite angle B is the side across from angle B. So, here's angle B. Opposite that would be side AC. So opposite means across from. Now we also look at adjacent sides. Adjacent side is the leg next to the given acute angle that is not the hypotenuse. You never use the hypotenuse as your adjacent side. It's one of the legs, not the hypotenuse. So basically it's the side the angle is sitting on. So the side that is adjacent to angle A is here, adjacent would be the one it's sitting on. So this would be adjacent to angle A. So that would be side AC. And the same thing for angle B. If this is angle B, the side adjacent to it would be the one it's sitting on, would be right here. This is adjacent to angle B. So that would be the side BC. So when you are given a right triangle, you should be able to identify the hypotenuse and which side is opposite and adjacent related to the acute angles that you have. That is the basis for the trigonometry that we are going to do this year. Now we are going to see how trigonometry is actually developed. In the year 1137, King Goodenough plans to attack the castle of the evil Lord Fetid. He asks his royal mathematician, Trig, to figure out how high the walls of the castle are. Trig measured out a distance of 16 feet from the wall and then carefully measured the angle of elevation to be 58 degrees. So he looked down here and went 16 feet from the wall, and he's going to be looking up at the top of the castle at an angle of 58 degrees. But he wants to find the height of the wall. He wants to find this right here. That is your x. So notice hopefully that this is a right triangle because we want the walls to be nice and straight. So that makes a right triangle, and 58 is an acute angle. So how can he find the height of the wall? He found a piece of parchment, preferably graph parchment, but any old parchment will do. He can use area of a smooth ground. He carefully draws a 58-degree angle. So this angle right here is 58 degrees that matches this angle up here. Now, measure any convenient length for an adjacent leg. So here's my leg right here. What would be a nice adjacent length? Let me see. Let's say this is 5. 1, 2, 3, 4, 5. So I want this distance right here to be 5. You can actually draw any length that you want. This will still work. And then draw the opposite leg. So this would be the adjacent side. So connecting from here to this side over here would be the opposite leg. All right, so there's my opposite leg. Okay, now, if we measure this length, how does this triangle, all right, so measure the opposite length, so let's measure our values here. 1, 2, 3, 4, 5, 6, 7, that's almost exactly 8. So let's say that that's going to be 8 for the opposite leg. All right, now, these two triangles that I just drew, if I drew in this opposite leg right here, hopefully I drew this perpendicular. What do we know about these two triangles? Well, this angle corresponds to this angle, and the right angles are the same right angles, so these triangles are similar. By angle, angle. So if they are similar, can't the ratio of the sides be the same? Yes, they can. All right, so we are going to set up a proportion comparing the sides. We are going to compare the opposite side that we drew in to the adjacent side that we chose for each triangle. So opposite side to adjacent side from the angle that we chose. All right, so let's start with the triangle here. From here, the opposite side is going to be my h or my x, whatever I want to use. And my adjacent side is going to be 16. In my similar triangle over here, my opposite side we measured was 8. If I counted up to here, it's almost exactly 8. And my adjacent side is 5. Can I find the height of the triangle? Sure I can. Cross multiply. 5h is equal to 16 times 8, which is 128, because I cross multiply here and here. And divide by 5, and h is going to be 24.3 feet. So Trig just created a way to figure out what the height of the castle is without having to actually whip out his ruler and measure it. It's kind of dangerous to do that. So the height of the castle is approximately 24.3 feet. All right, now King Goodenough moved on to attack the castle of the vile Baron Malodorous. Malodorous has a 15-foot wide moat around his castle. Goodenough asked Trig how long a ladder must be to reach from the far side of the moat to the top of the castle wall. Trig measured the angle of elevation be 71 degrees. What length of the ladder is needed? Okay, so let's look at what he did here. Here's his picture. He's looking how long this ladder right here is going to be. So that's going to be my x. So on graph paper, Trig drew this picture out. He measured a 71-degree angle. Now, measure any convenient length for the adjacent leg and then draw the opposite leg. So I'm going to measure, let's use 5 again. 1, 2, 3, 4, 5. So here is my adjacent leg is going to be 5. And when I draw this up, nice straight line, make sure it's nice and straight, which I'm not drawing. There we go. All right. So when it meets this point up here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, maybe 14.3 goes to about there. All right, or 15.3 or 14.3, let's say that's 14.3 as there. All right, now for the hypotenuse, I need to measure this. Now this is these tick marks are 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, let's say 15.3 approximately. All right, I'm kind of guessing on this one, but let's look at that one. All right, now we have the convenient length for the adjacent leg, and draw the opposite leg, and then measure the hypotenuse. We said the hypotenuse was 15.3, and set up a proportion and solve. All right, so we need to know what the ratio of the hypotenuse is and the adjacent leg. So let's do adjacent is to hypotenuse as adjacent is to hypotenuse. All right, again, because this is a right angle and this is a right angle and these two angles correspond, then these two triangles are still similar. So the adjacent side of this triangle is 15. The hypotenuse is x. The adjacent side of this triangle is 5, and the hypotenuse is 15.3. All right, so cross multiply and solve. 5x is equal to 15 times 15.3, which is 229.5. And divide by 5, x is equal to 45.9 feet. So that means that the ladder has to be 45.9 feet long. That's a long ladder. Okay, so using the ratio of the hypotenuse, adjacent side and the hypotenuse, we figured this out. All right, now let's try one more. So, King Goodenough next planned to attack the castle of the foul Count Flatulent. Before attacking, he wanted information about how well Flatulent was prepared to defend his castle. With an idea about 6.5 centuries before its time, Trig suggested setting up a spy in a hot air balloon. The balloon was tethered at the end of a 75-foot length of rope, which made an angle of 47 degrees with the ground. The king wanted to know how high up the balloon was. Okay, so when you're looking for how high up the balloon was, you want to measure the distance from the balloon perpendicular to the ground, because it's the altitude, how high something is. So this should be a right angle down here. So Trig got out his graph paper again, and he drew a 47-degree angle. So let's go down here. Here's his 47-degree angle. And you want to measure any convenient length for the hypotenuse. So here's my hypotenuse. It's nice and tick marked off, so I'm going to use 10. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be my hypotenuse right there. So where that made that dot. All right, now I want to draw the opposite leg. All right, so from this dot, I'm drawing down the opposite leg, right like so. Okay, so there's my opposite leg. All right, so I need to know how high up this is. So counting from here, I know that this is 1, 2, 3, 4, 5, 6, 7, and a little bit more. Let's say that's 7.3. It's approximately 7.3. It's not quite halfway, so 7.3 is that distance. Okay, so what we are comparing here is the hypotenuse and the opposite leg. So we are setting up a proportion of the opposite leg to the hypotenuse from the 47-degree angle. So opposite to hypotenuse in the two triangles. So these two triangles are similar, again, because the two angles corresponding are congruent and the right angle is congruent. So if we are looking for this height right here, that corresponds to the opposite side. So using opposite and hypotenuse, this triangle, opposite and hypotenuse, is 7.3 over the hypotenuse is 10. The other triangle, opposite the 47-degree angle, is x. The hypotenuse is 75. So this is x over 75. Cross multiply. We get 10x is equal to 73 times 75 is 547.5. Divide by 10, and x is going to equal 54.75 feet. So what he just figured out is that this height is 54.75 feet. So the balloon is 54.75 feet in the air. All right, so by now, Trig was really tired of drawing and measuring similar triangles so he could find the ratios he needed. He thought how great it would be if somebody made a table of opposite to hypotenuse, adjacent to hypotenuse, and opposite adjacent for all angles from 0 to 90 degrees. He went to the King's Library and found that some Greek guy named Hipparchus had the same idea over 1,000 years before. Trig copied the table and took it home to practice some problems on. So let's take a look at his table right here. There's his table of trigonometric values. That's the sheet of paper that I gave you. We are going to use these ratios that are here to solve for the missing sides in the triangle. So take a look at the table, and we will be using it tomorrow to solve these problems to find the lengths of the sides and the angles in these triangles.